I'm Mr. Ish and I'm welcoming all of you to this video where we are looking here at this concept of the inductive effect. Thank you for joining me. What is inductive effect? It's something you will look at in the earlier chapters of organic chemistry. It's a basic concept, but let's look at it very briefly. We are looking here at a transmission of a charge which can either be a positive or negative charge through the sigma bonds connecting a variety of atoms along the chain of atoms. We're looking at the charge transmitting along that chain of sigma bonds. In essence, it is affected by electronegativity of the atoms which are seen along that chain of atoms and the distance of those electronegative atoms from that atom which is either bearing a positive or a negative charge. When you're thinking about this positive charge on an atom, what does it represent, and a negative, what does that represent? Think about it always in the following way. When you're looking at a positive charge on an atom, it represents a charge deficiency. When you're looking at a negative charge on an atom, it represents a charge excess. So keep that in mind. This concept is important because it enables the student to predict acidities and basicities of a variety of organic compounds. In addition to that, it does have a variety of other purposes, but as the typical chemistry student, you'll be using this concept here to determine or rank compounds with regards to their acidities and or basicity strengths. Look over here, ethanol, CH3CH2H. If you were to deprotonate this, you know what you would end up with? A ethoxide anion, and I'll write it out for you. It's ethoxide anion. You have taken the ethanol, you have deprotonated it. Now you have an oxygen here bearing a negative charge. This represents here a charge excess. You have a high charge density on that oxygen. Inductive effect can help you predict the strength with regards to this type of a compound. If you were to reprotonate it, what would be the relative acidity of that? Well, it would depend on what you have. When you're looking over here, you're only looking at alkyl groups, CH3, CH2 groups. You're not seeing anything electronegative. That's not necessarily a good thing because it destabilizes this negative charge. Why would it destabilize it? Let me show you two instances. Look over here at this compound. I have here a tertiary alcohol, a alcohol bound to a carbon atom which has a tertiary structure or tertiary characteristic because it is bound to three other carbon atoms. It's a tertiary carbon. Compared to this original item which I showed you here, ethanol. Here the hydroxyl is bound to a carbon which is a primary carbon. It is bound only to a carbon other atom. Now alkyl groups have a tendency to donate electrons, so they're donating charge into your system. If you were to look at this and deprotonate these, and what you would be looking at would be your deprotonated atom, oxygen atom. Now you're looking here at an oxygen with a relative charge excess. If you're looking over here, the alkyl groups tend to donate. That's their habit, they're donating. When you're looking over here, you have three alkyl groups, three methyl groups which are donating into an area which is already excess of charge, and that's the oxygen. What do you think would be more unstable than the other? This right here would be relatively stable. This here would be less stable simply because you have too much charge being donated into an oxygen which already has excess of charge, so it's unstable. This right here is relatively more stable. It would tell you now with regards to that, because you are having a charge donation by means of induction along sigma bonds, you could clearly say now in terms of acidities that your ethanol, which would be CH3CH2OH, would be more stronger of an acid than this other alcohol, which we can say is tertiary butyl alcohol. This right here is more acidic than that, even though in terms of acidities these are not relatively considered acidic compounds, but in terms of organic acids this would be more acidic than that because you have, in terms of their oxides, the negative charge oxygen atoms generating, this is more stable than this. Here you have too much oxygen bearing too much charge, too much being donated to it. Here you don't have as much being donated to it, so it's less unstable than that, so it's relatively more stable. This would be more acidic than that. Now how can we bring inductive concepts into this? I'll show you. Look at this next compound. We're looking here at butanol, CH3, CH2, CH2, CH2OH. Butanol, butane with an alcohol, butanol. I'll take this, I'll convert it into CH2, and I'll bring in a chlorine. Now I have a bunch of sigma bonds over here. This right here would represent a charge excess, especially if you were to deprotonate it and make it like that. I have an electronegative atom. It would have the tendency to start sucking away, and it would start stabilizing that oxygen by making it less excess of charge. You have so much over here. These alkyl groups are donating to it, but now I have an electronegative atom which is pulling away by means of an inductive effect. I have a withdrawal of charge, excess charge from the oxygen by means of sigma bonds, the chain of sigma bonds, because of this electronegative atom. This would right here would make that oxide more stable. What would happen if I had thrown in here another chlorine atom? Well, it would make it even more stable. What would have happened if I had brought in yet another chlorine atom? It would be even more stable, because now I have 3 electronegative atoms sucking off that oxygen. But look at the distance of these chlorine atoms from that. I am 1, 2, 3, 4 carbons away. This right here is relatively stable, and it's making this oxide stable, but not so as much as this next example as I show you, where we're still looking here at this butanol, CH3, CH2, CH2, CH2OH. I convert it into an oxide, and what we have is this. Now what I'm doing here, I'm bringing my chlorine atoms right over here. I have 2 chlorine atoms, but they're located less of a distance away from the oxygen bearing the excess charge, and I'm seeing an inductive effect towards the direction of the electronegative chlorines. This would be relatively quite stable, because now the distance has decreased. Our inductive effect is more likely to happen because the distance from that excess charge is less. As the distance of the electronegative atoms from that excess charge increases, the inductive effect decreases. As the distance decreases, the inductive effect increases, and the presence of these electronegative atoms next to a charge excess will help in stabilizing it. Let's talk about how all of this affects in terms of acidities. I have 4 compounds over here. I'm looking here at a cyclohexanol or cyclohexanol. Here I'm 1, 2, 3, 4 chlorocyclohexanol. Here I have 2 chlorocyclohexanol. Here's my 1, 2, 3, 4, 5, 6. I'll have 2, 6 dichlorocyclohexanol. How would I rank these in terms of acidities? Even though alcohols are not relatively acidic, but you can rank them because we're looking here at inductive effect. Inductive effect depends on the presence of electronegative atoms that would help stabilize the excess charge on your oxygen. Once it became deprotonated, this is what you would have. How can you stabilize this excess charge? You can by sucking this charge away from that oxygen by means of electronegative atoms. I'm looking here at a compound which has no electronegative atoms. Here I have 1 which is chlorine, here I have another chlorine, here I have 2. But look here at the distance. I have 1, 2, 3, 4. I'm looking here at a chlorine which is 4 away. I'm looking at a chlorine, this is 1, 2, which is just 1 here. I'm here 1, 2, 3, 4, 5, 6. But both of these chlorines are so close to that oxygen. If you were to rank these, then you're looking at that compound which has the highest number of electronegative atoms and closest to your oxide, which would be again your this. You want to have your electronegative atoms closest to an oxide, and I'm seeing that right over here. If I were to call this structure D, this right here is A, this here is B, then C, then I can start ranking these in terms of inductive effect. I'm looking for electronegative atoms, many in a certain compound, but closest in terms of sigma bonding to your oxide, and it's D. And D would be most acidic, followed by C, because when you compare B and C, C's chlorine atom is closer to your oxide when it would develop, which would be stronger than B, which would be stronger than A. This right here would be your acidity in that direction, and we've used the concept of inductive effect to help us out. Now let's look here at something in terms of basicity. Now let's talk about basicities with regards to inductive effect. If I'm looking here at ethylamine, I have an ethyl group attached to an amino group, and I were to protonate this in the presence of an acid, what would I have? CH3, CH2, I'll have here NH3 plus. I have a lone pair of electrons, but they've been lost because I've protonated. I have 2 hydrogens, now I have 3 hydrogens. That positive on that nitrogen represents a charge deficiency. Charge deficiencies are not good because now your atom is starving for charge. How can you stabilize an area of charge deficiency? Well, that compound should have atoms which would donate by means of induction through sigma bonds and fulfill that charge deficiency. Alkyl groups, which are basically these carbon atoms, help to donate because these are electron donating groups. That's what they are, electron donating groups. Electronegative atoms, which I'll write as electronegative atoms, they pull charge away and they are electron withdrawing. Electron withdrawing atoms are bad when you are dealing with these type of bases, but electron donating groups are good. You want to see that, you don't want to see electronegative atoms. When I have something like this, I know I'm looking here at an alkyl group which is attached to this charge deficiency and is helping by means of donation through induction, and it's stabilizing that charge deficiency. The more of alkyl groups I can have on that compound, the better it is. So let's start understanding inductive effect with regards to basicities. I'm looking here at tertiary butylamine, and I'm looking here at ethylamine. Which one is a stronger base? If you were to look at the protonated form of the nitrogen, you know it would be something like this, where everything is now attached and the nitrogen has lost its lone pair of electrons. In that particular case, you have a deficiency here of charge on nitrogen. You want items which are donating charge by induction, which are stabilizing that deficiency, and that would be preferable. Here I have alkyl groups, here I have alkyl groups, but here I have fewer, here I have more. I have three areas here through which I have charge donation by means of induction, which are stabilizing an eventual protonated form, and this would make it a stronger base than that. Here I only have charge donation by induction from one side. Tertiary butylamine would be a stronger base than ethylamine, simply because a protonated version of that amine would be more stabilized by means of charge donation through induction. Look at these two examples. I'm looking here at an ethylamine which I will modify, and it looks something like this. This is what I have, but I take out one hydrogen and I bring here a chlorine. So I'm looking here at 2-chloroethylamine, and I'm comparing it to the CH3, CH2, and then NH, and then I have here a CH3. Here I have a methyl or ethyl. You can say N-ethyl, N-methyl. We'll name it properly. N-N-ethyl methylamine. That's what it is. N-N-ethyl methylamine. Or you can just say, for simple purposes, ethyl methylamine. I have an ethyl group attached to an amine. Here I have, this is carbon 1, this is carbon 2. I have here 2-chloroethylamine. That's what I have. It's understood the amine is attached to carbon 1. 2-chloroethylamine and ethyl methylamine. What do you think is a stronger base? I have over here in their protonated versions, when I'm looking at a protonated amine, it would be like this, a charge deficiency. I'm looking for something which is going to donate to it. I have two alkyl groups that are going to donate to that eventual charge deficiency. Here I have one alkyl group, but I have an electronegative atom which will pull away. It will destabilize that charge deficiency by making it even more charge deficient. These will help donate to that charge deficiency. Ethyl methylamine will be a stronger base than this chloroethylamine, simply because I'm looking here at a chlorine atom which is ruining it in terms of your eventual charge deficiency, and you cannot stabilize it through induction. Let's look here at another example. Look at the difference between these two. I have here chloroethylamine, but I have two chlorines, and then I'm looking here at a 1,2, so I will say 2,2-dichloro, and then ethylamine. Here I have 2-chloroethylamine, one chlorine atom. Here I have two. When I'm looking at the eventual protonated version of the nitrogen, which is a charge deficiency, and I want things to come through it in terms of charge, I want electron charge to come through that nitrogen through sigma donation or inductive effect. I won't be seeing too much of that here because I have two electronegative atoms which are sucking the charge away. Here I have one. Even though these are relatively non-basic, which one would be more basic? It would be this with the single chlorine atom versus here the two. This would be more acidic than that. This is more basic, this is less basic, simply because in the protonated version I have less destabilized nitrogen. Here I have a very greatly destabilized nitrogen because of the presence of two chlorine atoms. And you could imagine if these chlorine atoms were located closer to the nitrogen, the distance is less, then the withdrawal effect would be even higher. Look at these four compounds A, B, C, and D. I haven't thrown in any electronegative atoms because you know the predictability of that is easy. We're looking here at only electron donating atoms and or compounds attached to that amine group. I have here cyclohexane attached to your amine. I have here a cyclohexane with a methyl attached to the amine. I have a cyclohexane with a methyl here, and that amine. A methyl attached to the amine, cyclohexane, and a bunch of other methyl groups. Now here you're looking for a eventual protonated amine, which would look something like this, with a charge deficiency on that nitrogen, and it wants to find atoms which are going to donate by means of electron donation through sigma bonds via induction. The more of those electron donating groups there are, the better it is. Here I have very few. I only have a cyclohexane. Here I have a cyclohexane with a methyl, so it's an extra additive effect, which is good. Here I have another methyl group. It's good. All of this is going to donate through that. I have here a methyl group. I have a methyl group over here, and I have this methyl group right here. If you were to start comparing in terms of bases, the C happens to be most basic because it has the most in terms of inductive effect, in terms of alkyl groups available to stabilize an eventual protonated charge deficient nitrogen, followed by what? This would be next more basic, then this right here would be most basic after that, and finally A right here, cyclohexylamine, would be the least basic because you have the least amount of induction going on over here. It's still good, but not good enough as these other compounds show. So here's your basicity because you have the highest amount here in terms of electron donating. And you have a methyl here which is located relatively close. Here you have a methyl located further away. If you were to compare between C and D, automatically C wins. Hence it's more basic than D, which is more basic than B, which is more basic than A. And with that, let's close out very quickly with this, where we have a bit of a difference. We're not looking here anymore at a primary amine. In all the examples I've given you, we've had some sort of R group which was attached to your amine, and that amine was attached to hydrogens in addition to an R group. But here, look at it. We're looking at an amine where you have R groups attached entirely around that nitrogen. You of course have those lone pair of electrons. We're looking here at examples of this form. If you were to compare a amine of this form and an amine of this right is a tertiary amine, this is a primary amine. The tertiary amine is a stronger base than a primary amine simply because you have more electron donating groups all the way around the nitrogen. Here you only have one. The tertiary amines are better, stronger bases than secondary amines, which are better than primary amines, which is better than just ammonia on its own, NH3. A secondary amine you can imagine to be this. You'll have an R group, a nitrogen, another R group, a hydrogen, and that would be it. That is secondary amine. This is a primary amine. Here's your tertiary amine, which has 3 R groups around that nitrogen. And of course NH3, you don't count that as an amine, it's an ammonia. But you are seeing over there in terms of basicities, tertiary amines are stronger bases and secondary than primary than ammonia. Let's look here very quickly at this example, 3 compounds A, B, and C. All of these are tertiary amines, and you know at the end you're looking here at a protonated amine which would look something like this, and it would be charge deficient. You would lose the lone pair of electrons and you would protonate it by means of a hydrogen, as you can see, and we have that charge deficiency. Which one of these best stabilizes that deficiency of charge? It's the one which has the most bulky R groups. You're looking at methyl all the way around, you're looking at cyclohexyl all the way around, here you're looking at cyclohexyl methyl all the way around. Methyl cyclohexyl all the way around, however you want to name it. But anyhow, if you're looking at it clearly, you see this group over here is more bulky than that group, which is more bulky than that. It clearly tells you, because there's no other difference other than that, the C compound will be a better base, stronger base than a B compound, which will be a stronger base than a compound, simply because you have best charge donation through inductive effect. You can see it going all the way through, as you will see. The most R groups giving charge stability to an eventual protonated amine, which will be deficiency, a deficient status, versus something like that, versus something like this. These are all good bases, but this just happens to be a better base than B, which is a better base than A, and you can see it, and that right there is your basicity trend. This right here is in terms of base strength. C stronger than B, stronger than A. And with that we close the video. Thank you for watching.